introduction of myself. I think I have been already introduced by the host, so not much to say. So I'm associate professor at Tongji University. I'm also external professor in a university in Spain, a university in South America, and recently I'm the general secretary of the IEEE Vehicular VTS Propagation Committee. Yeah. So I have divided my talk in 5 parts. First, I will tell you a little bit the motivation, why we do the research we do. Then I want to tell you how did we start on this. This was already almost 15 years ago. What we are doing in the currently and what we will do afterwards, and then just finish with some conclusions of the work. So starting with the motivation. So most of the work I have been doing in the last 15 years is related with the communications for vehicular environments. I like to say that this was defined in this paper here. I like to say that the society is now like lots of people traveling from one place to another. So most of us, we work maybe in the city center, but we live in suburban area or the other way around. For example, for myself, I live in Yampu district. I need to go to Yalin district every day. So I need like 1.5 hours one way. And every time you take a public transportation, you take train, you take subway, you see everyone using their devices and so on. So everyone expects that no matter you go at 300, 400, 600 kilometers per hour, you can use your phone and you can talk to your family or do some work or something like that. Even more important than that, nowadays, especially with the boom of the autonomous driving and so on, so the communications is not only between people. Communications are between machines. So the cars communicate with each other, they communicate with the roadside elements, and everything needs to be connected in order that the transportation is safe and the transportation is efficient. This is good, of course. We are seeing advances in autonomous driving and so on that we have. But also we have the problem that communications give us support, technological support for our activities, daily activities, but at the same time, they make us very dependent. So for example, nowadays, if the network is down, if you take a high-speed train and the network is down, the high-speed train will stop automatically. Even the pilot wants to start the high-speed train, he or she will not be able to do that, okay? Because for safety, there are the safety communications of the train. They will not allow the car to run. So, in this presentation, I want to tell you how our research evolved and how we use software-defined radio in the evolution for evaluating from 4G to 6G. So we are going to start maybe around 2011, and we are going to finish in the current days and what is going to come in the future. So how did we start this? Well, as I mentioned, we started this around 2011. It was when I started working in this topic. At that moment, in 2011, I don't know the current situation in China at that moment, but at least in Spain, we were starting to deploy LTE 4G network. And in 4G, in the standard 4G, one key case for communications is the high-speed train for vehicular communications. So why this was an interest in 4G? Well, in general, as I have mentioned, everyone wants to go in the train. To go in the train at high speeds and still be able to use the phone and so on. However, the most important thing is not that. The important thing is what we call critical communications. These are communications related with safety. So there is a whole protocol. It's called GSMR. It's like GSM for radio, for radio, sorry. And this protocol defines all the different communications needed in the train and in the high-speed train. Like, for example, there are communications like to send a command to the train, like to say, okay, there is going to be an object in the railways, in the rails, so you need to stop, or something like that, or communications between the crew of the high-speed train. There is a whole standard defined for that. Now, the problem is that in 2011, so GSM was already at the end of its life. I think we started with GSM like in the end of the 80s. So like at the beginning of the 80s, we have the mobile phones that are analog. Then like the end of the 80s, we have the mobile phones that are digital with GSM. And the thing is that this was already like 20 years later, and the trains were still using GSM. It's already difficult at that moment to get GSM equipment. So and it was very expensive to keep this. So we wanted to know whether we could use LTE to replace GSM for high-speed train communications. Okay, I want to mention something as a as a motivation, a sad motivation for this work, which is what we show here in this picture. What we have here in this picture was in 2013, just more or less when we were starting with this work. It was the worst train accident in the history of Spain. It happened in my hometown, in fact, just 60 kilometers far away from my home. What happened here is that there is this curve here. This curve is supposed to be taken at 80 kilometers per hour, maximum speed, but there was a communication between the pilot of the train and the head of the next train station. The reason was that there are some passengers with some special needs, and the train needs to change from one track to another track. Due to this call, the pilot was misled, and he didn't brake on time the train. Okay, we have the safety measures. It's called ERTMS, that it can stop the train. It can send messages to the train autonomously to stop the train. But at that moment, the communications, the railway communications, they were shut down. They were stopped because they were experiencing some problems, so they just shut down. Due to the lack of communications, we had this accident here. The train did not stop on time. We have this accident here. 88 people died. So when I say, can we use 5G to replace GSM? This is not a trivial question. It needs to be proved. It needs to be statistically proved that if we change from GSM to LTE, to 4G, let's say, from 2G to 4G, the system will work reliable, and we are not going to have this kind of situation. So at that moment, when we started this project, we didn't know. So the answer was, we don't know. They asked us, okay, can we use LTE to substitute GSM? And the answer is, we don't know. You may think, okay, if you can use 2G to control a train, of course you should be able to use 4G, right? Because 4G is much better than 2G. So if 2G can be used, 4G has to be used. Well, the answer is not so simple, because maybe 4G is much better than 2G to transmit a lot of information very fast. But maybe to transmit some packet that is scheduled to be transmitted in some specific time, and this time is, it needs to be that time. It cannot be later, because otherwise we are going to crash. We don't know. This is something it needs to be proven, and something it needs to be statistically proven and tested. So what is the answer? Well, as I told you, in 2014, the answer is, we don't know. We don't know. But now the answer is, yes, we can. We can use LTE to substitute GSM. Okay, how did we reach this answer is how I want to start my talk. So I'd like to show this sentence. This sentence is by Lord Kelvin. If you have the opportunity to go to Glasgow University in the UK, please visit his museum. It's very interesting for metrology. And he usually say this sentence, which is a sentence, quoted as this. It says, if you cannot measure it, it is not science. This is a sentence I tell many times to my students. So, as I told you, we need to prove whether LTE can substitute 2G for high-speed train communications. Nobody has done that before. Can we rely on simulations? Well, we certainly can do simulations, but would you get on a plane that was only tested by simulations? I don't think so, right? Nobody wants to go in a transportation vehicle to put your life in this transportation vehicle if the things were just tested by simulations. So how did we prove that LTE could substitute GSM? Well, we measured it. We actually did the measurements, and we did enough measurement campaigns, so our results are statistically significant, and we can prove that. However, how could we do that in 2011? In 2011, you could not go to the shop and buy a 4G phone. There is no 4G phones available. The network, the 4G network, just started to be deployed. So how could we do that? Well, the first thing we need to, that was the starting of my PhD thesis many years ago. So the first thing we needed to do at that moment was, okay, we need to create our own receiver, our own transmitter. So that was our first usage, our first contact with the software-defined radio. We needed to create a transmitter, and we needed to create a receiver that could transmit LTE signals and receive LTE signals, put the transmitter in the ground, put the receiver in the train, and do measurements. So we spent about 1.5 years doing this. For the hardware, we use USRPs. This is a picture of the USRP at that moment in 2011. And for the software, we create the so-called GTEC 4G simulator and GTEC 4G test. Okay, now we changed the name to 5G because we have extended to 5G, but at the beginning it was 4G. So we have created a software that can consider a random number of USRPs. Each USRP is a node. It can be a transmitter, it can be a receiver, and we can transmit either 4 signals to 5G signals. We can evaluate the physical layer of both LTE and 5G standards. It is very robust because it has been measured. It has been used for continuous measures, like more than 5 hours. And that was the starting of our path, of our work using USRPs and software-defined radio. Well, if someone is interested in using this software, you can download it here. It's available. We made it open source, and you have the documentation in this paper here in the bottom of the slide. So we tested. Before I ask, okay, can we use LTE to control a train? Well, the answer is yes. We have tested it. We have done the first evaluation of LTE communications for high-speed train in Spain. I don't know if it was the first one in Europe, maybe also, I don't know it, but it was the first in Spain. We obtained statistical propagation channel models, and we evaluate the performance of the communications, and we prove empirically that we could use 4G to control trains. Of course, this was a big project. It included 3 universities in Spain and included the railway operator in Spain and many other partners. Since we did all this work, we also use this system that we built to do tests in the subway. So these pictures are in the subway of Madrid. So we also proved that we can use LTE for communications in the subway of Madrid, and we even did the tests in the car. So at that moment, so you see nowadays is in a mode, communications in car, like for autonomous driving and so on. In 2011, we were already testing car LTE 4G for cars communications at that moment. The problem was in 2015. So in 2015, we have already proved that, okay, LTE can be used for high-speed train communications, but what happens in 2015, 5G appears. So now the question is, again, can we use 5G to control high-speed trains? High-speed trains were, again, one key vehicular environment for 5G, for the 5G standard. And again, we could say, okay, if you could use 4G, of course you should be able to use 5G to control high-speed train. It should be possible. But the reality is that these things don't work this way. You need to certify it. You need to do a statistical analysis, and you need to prove, okay, the error rate in transmitting packets is lower than whatever percentage established by the Railway International Union. Well, how did we do this? Well, we did it again by measurements. As I mentioned before, we don't rely on simulations, or we rely on simulations, but before doing simulations, we need proper simulation models. We need accurate simulation models, let's say. In order to do that, we need to first do measurements. The problem is that in 2014, or let's say, when we tested LTE for high-speed trains, the most important thing we have learned, you know what it is? It's not that we can use LTE for high-speed trains. The most important thing we have learned is it's super expensive to do these evaluations. So in order to do the evaluation of 4G for high-speed train, we needed to measure 2 nights. And in order to measure 2 nights, we had a project of 3 years. So we were 3 years working just to do a test in 2 nights, 10 hours in total. We need to rent a high-speed track. We need to stop all the trains in that area of Spain. We need to rent a high-speed train. We need to have a pilot, and we need to mount our own base stations, and we need to ask the network operator to shut down their own base stations. In 2015, we could not do this anymore. Now there are too many people using 4G. There are too many trains. We cannot stop this. So we just realized we cannot test 5G in high-speed trains anymore. It's just too expensive. We cannot do it. It's impossible. Then we decided to become creative. So at that moment, I went for about 1 year to the Technical University of Vienna in Austria. And then we introduced our software-defined radio to this measurement equipment here. So we designed and created a rotating antenna like this one. So this is our antenna, actually 4 antennas here, and we have a pole, and this pole can rotate at any speed between 0 and 560 kilometers per hour. And this way, we can evaluate the communications at the different speeds. So it's like every time we rotate this antenna, we do 1 circle, we have 1 channel realization. And we can have this channel realization, exactly the same channel realization at different speeds, because we can rotate this very precisely at different speeds. If you think that that is not possible, I have a picture that proves that this thing has been built. This is the picture. Here you are the antennas, and this is the pole rotating. So what we did, and of course, what we did with this is we have this was the receiver, the transmitter. We put it just still, and this was the receiver, and we connect this receiver to our system, our software-defined radio, and did measurements. And this was how we did the first evaluation of 5G communications for high-speed environments in Europe. It was in 2015, and it was the first time someone proved that we could safely use 5G communications in high-speed scenarios. So this way we prove, yes, we can use 5G in a high-speed train, and it's safe to substitute all our 2G or 4G equipments to use in the high-speed train. So that was a little bit of the past. And what happens now? Well, we're still in 5G, right? And but 5G, we already proved that we can use 5G for high-speed train. So what it comes after high-speed train? Well, you all know this character better than me, fly, right? Well, actually, 5G introduced another big need, another big milestone for vehicular communications, which is the unmanned aerial vehicles, drones, UAVs. As you know, due to, especially in China, drones are used for many applications due to their decrease in size, in cost, and so on. They can be used for rescuing operations, for topography, precision farming. Of course, all these applications require communications. Actually, there is a specific key application in the 5G standard, which is to use the UAVs not only to receive data, but to use them as a base station when there is some disaster. For example, imagine there is an earthquake and the infrastructure for communications is destroyed or partially destroyed, and then we need to give service to people so that people can call the emergency service, people can call the police, people can call the ambulance, and they can get some proper assistance. So in around 2017, or 2016, maybe end of 2016, beginning of 2017, it was introduced by the 3GPP, the need of evaluating whether we can use 5G to communicate with UAVs. And then the question is, as before, can we use 5G for safe UAV communications? Or in other words, can I use a 5G phone? Can I control my UAV just from a 5G phone safely? It's like my UAV will not crash. Let's say if I send a message to UAV, please stop flying because you are going to crash a building. Will the UAV receive this message on time? Well, how did we solve this? Well, again, we did measurements. This was another huge measurement campaign. We put our software-defined radio, our USIPs, in our UAV. We put one antenna in the UAV, and we created our own base station, also with software-defined radio. This is a USRP. This is the antennas used for the transmitter. And we did a super extensive measurement campaign in our campus, a suburban area in Jadin. This was a big set of works together with some university in the US, some university in Denmark, in Sweden, in Madrid, in Korea, and several commercial partners like Huawei, ZTE, the German Aerospace Center, the ETRI. And this was the first time it was proved that the 5G network could be used to control UAVs. So there is some regulations from the FAA, the Federal Aerospace Aviation in the US, and they establish like the requirements on reliability, like how many packets you can lose for every million packets you send, the reliability, the delay, like I send a command to the UAV, how fast this command needs to be successfully received by the UAV. All this is specified in order to ensure a safe operation of UAVs. Well, we did the first work in which we prove that we can use 5G with these reliability constraints in order to control directly the direct 5G signal in order to control the flight of UAVs. It's not that we can use it in every condition, but there are some constraints about the link distance and the scenario and so on. We have established these conditions, so we know whether we prove under which conditions we can use 5G to control the flight of a UAV. And what is coming now? What are we working now? What is the future for us? Well, the future is 6G, right? 5G is already well mature. Now we are starting with 6G already for several years. 6G is supposed to be in the market in 2030. So there is not much time still to work on the standards of 6G. And the one big promise of 6G is what we call, sometimes you see it as a joint communication and sensing, sometimes you see it as integrated sensing and communications. It has different names, but the idea is your phone or your receiver is not only a receiver, it's not only communicating, is also like a radar, is aware of the environment. So one typical scenario for this is the autonomous driving. So this picture you see here is for one autonomous car, all the sensors we have. Different colors correspond to different sensors. We have cameras, we have LiDAR, we have a lot of sensors. How if we could substitute all this just by using our 5G receiver in the car? And this 5G receiver would be able to receive the communication signals you need, like for, as we said before, for autonomous driving, you need communication signals. But how about if we use this communication signal also to detect the objects in the environment? How about we don't need all these sensors, or at least we can reduce a lot of sensors? Maybe in the car it doesn't matter much, okay, because a car is a big thing, it's maybe 4 to 5 meters long, you have space to put a lot of sensors. Electricity consumption is not a big issue because you have big battery. The engine of the car consumes much more than these sensors, so you don't care so much. But how about a UAV, for example? In a UAV, you have very limited autonomy for flight, maybe 15 minutes, something like that. If we install here like 6 different sensors to do sensing, it's like we have a lot of weight on the UAV and we have a lot of processing needed, a lot of computational processing needed. So all these will consume energy. Finally, maybe you can only fly for 5 minutes with the UAV. Nobody likes that, right? How about if the same antenna we use for communications can be used just to sense the environment? Well, that's the works that we are doing recently. So recently we are working on sensing using the communication signal to get information of the environment. This example here, so this happens when you put a logo of our university like this, okay? You have a metal version of our logo, you put it, for example, inside an envelope, you cover it, okay? And you put it in front of our receiver antenna. And just with the signal that we receive with the base station, we are able to obtain this image here. Of course, it's not perfect, but you can see that the shape resembles clearly the logo of our university. Another application that we have been using is with UAVs. UAVs is one of our key topics. So this figure you see here are some preliminary results showing this paper here, in which we detect the main objects in the environment. So we have a UAV, the UAV flies, receiving the communication signal, and just with this signal that we receive, we are also able to find the big buildings or the big elements in the environment. Well, currently, this work was initial work based on some measurements we did in 2018. At that moment, we have a small UAV with only one antenna, and our software-defined radio at that moment, we can only afford to transmit around 20 megahertz bandwidth, and only one channel in the transmitter, one channel in the receiver. Recently, in the last year, we have been working closely with LuGuang, and we have designed, together with LuGuang, in cooperation with them, we have designed this measurement system that I imagine here. What is this measurement system? Well, it's composed of 8 USRPs and a very powerful server, plus some clock distribution facilities and some signal generator. And what we reach with this is we managed to reach 16 channels operating in parallel with a bandwidth of 100 megahertz, and we can continuously receive signal without losing any sample for easily 15 minutes or 20 minutes or half an hour, something like that. So nowadays, we are starting to use this equipment. Unfortunately, we don't have any result that we can show yet, published, but we are using this equipment. So we have an antenna in the ground that we can receive 16 different channels. And we have upgraded our UAV. Our UAV now is a much larger UAV. It can carry up to 30 to 35 kilograms. So we can set also some USRP here, but not only with one channel. We are currently considering 4 different channels. So we have a system which is 16 times 4, 16 channels in ground, 4 channels in the air. And we are using that to test our algorithms of sensing. For example, this is just a very preliminary example here because, as I mentioned, this is a starting work. We have not published anything yet. And we can see that we can detect in which direction the signal is coming. So this is the azimuth, this is the elevation, and the color indicates the cold color indicates low power, hot color indicates high power. So we can see we are now able to distinguish where our signal is coming from. So we can distinguish, for example, here, if this is a representation, a digital representation of our campus, we can know where our signals are coming from, where the signals, in which building the signals are being reflected. In other words, we can do sensing, but in much more, let's say, in the works that we published in 2022, we can just detect roughly, okay, there is an object here, or there is another object here. But now, thanks to this multi-channel, multi-antenna system, we are able to achieve a very high angular resolution. We will be able to know exactly this, where all the different reflections happen. This is important for sensing. This is the basis of creating digital twin, for example. As mentioned, this is a work still ongoing. We have the great cooperation from LuGuang. And with this, I would like to conclude my talk. And just some remarks of my talk. Communications are a basic element for the society in motion now. All of us, we have very different kinds of vehicles, like autonomous driving, UAVs, trains, subways. All of them require these critical communications. And these critical communications, they need to be tested. Every time we get a new standard, like 5G and 6G, we get new capabilities, right? In 4G, it was communication for high-speed train. In 5G, it was communication for UAVs. In 6G, it's joint communication and sensing. Yeah, new capabilities. But in order to safely exploit these new capabilities, we need to prove, we need to test, we need to statistically prove that our communication system is reliable enough to support these new applications. In order to do this, empirical research is basic. Simulations are not enough. We need to prove that the models we use in simulations are accurate. The only way of doing that is measuring, experimenting. And many years ago, maybe 20 years ago, this was not, it was possible, but it was very complicated. It requires a lot of money. But nowadays, thanks to software-defined radios, thanks to solutions like USRPs, this becomes relatively affordable. We can easily reconfigure by software most of the parameters. We can use the same USRP to test many different communication systems. So undoubtedly, SDR constituted a reliable and affordable tool for the empirical research in our field. And with this, I finish my talk.